Hello everyone. So this is the integrated deformation profile. You have seen this image in the PPT. So we had three different versions of movement of ice mass, and in this case obviously the ice was moving from the right to the left. In my drawing here I'm going to show it from left to right, so this shouldn't just cause any trouble. I'm going to break this down into the three parts of motion, and I'm going to start by speaking a little bit about what causes these movements, what factors are included here, and just very briefly how the ice is moving at all. So here I say that what we have here is three different ways of movement or types of movement that can be combined in certain ways. Firstly, it's the thickness and the slope. So how thick the ice is, how high or how thick the glacier ice is itself, that will be a factor. Obviously the slope, so that will be the first component here on its own. To what extent the ice is going to be moving, deforming as a mass itself. And then warm or cold base will be a component here, the second one. So to what extent will it be sliding? And the third part is rock bed or sediment bed. So what is this actually made of? The bed on which the ice is moving, because if it is a sediment bed, that can be also moving, deforming it itself. We'll talk about this more in details in this class. So that's the third part here. And just to very briefly say how the ice mass itself can be moving, here we have this cross section, which means the ice is moving basically towards us. So this is the U-shaped valley, just to understand it very briefly. And so what is the pattern of movement? It's not going to be deforming on its own, just very simply as it is here, but on the side of the bed, so in the glacier valley, over here, obviously there will be much of a friction, so there's a drag that will slow down the ice. We know that it will be actually over here in the central or midline of the glacier will be a fastest. And interestingly, the pattern here in this change of speed would be something like this. So it's going to be the slowest on the top and on the side. It's also going to be quite slow over here in its motion, in its transformation. But later on, it will be something like this. What I mean by drawing these is that the speed or the velocity and the change in velocity will be not equal depending on where we are from the side of the glacier valley, because on the bottom it will be somewhat faster. So on the side it's going to be slower. What is the reason for that? It's basically the thickness that over here in the central line will be a higher volume, and so that pressure, that force will cause the ice to deform and move over here in a higher rate than over here, for example, where this amount of ice that would cause this pressure would be missing. So this is an image that also is in the PPT. Just to recap that it's not completely equal in its movement depending on where we are. And also we can express this in like a longitudinal pattern. So this movement will also look like, if the glacier in this case is moving from the left to the right, on the top it's going to be the fastest over here, and also just following this kind of pattern, the speed will slowly drop and accelerate over here in its drop. So what does it mean? That the ice, as we said, will be moving relatively fast here. It will be carried by this whole thickness, and the slope itself will cause the movement to be the fastest on the top. It's basically the drag, the friction that will be missing on the top. That's why it will be fast. And over here there will be another component, which will be actually the weight, that will still make the movement faster than if it would be something like a linear change. But over here on the bottom, on the base of the glacier, it will be definitely the friction and the drag again that will be the main component in driving this movement. So that's why we just want to know that the ice is not going to be moving in an equal way depending on where we are within the valley, or within this cross section, or in a longitudinal pattern. Okay, so just to put this down then, what we need to speak about is just to have a larger picture here. In the first place, we can say that the ice is going to be moving, again in my little drawing, from the left to the right. And if we start by looking at a point on the top of the mass in the first place, that will be moving the fastest, possibly again depending on the thickness and the slope at a certain rate. We can say, like, just to put something here, 30 meter per annum per year, just to put something over here. And again, we said that it might be moving in such a pattern like that, or even more, to be perhaps more precise, something like this. So the more we go towards the top, perhaps it will be a little bit more linear. And so this is the first component of our movement. This will again depend on the thickness and the slope. So the thicker the ice, the faster the transformation, and also the slope, this deformation, this transformation of the whole mass itself will be again faster. But anyhow, the next point can be thinking about warm and cold base. So I'm just going to show it over here. If we have a glacier with a warm base, that will mean that over here it will be sliding on the bed, so there will be less of a friction. It will be able to slide if it's wet. Now, we were talking a little bit about what this warm or cold means. It will often be about the pressure and the pressure melting point. So depending on the weight, or also the shape, the pattern of the bed, it can melt the mass itself by its own weight. So then we say that here perhaps there can be a sliding of, just randomly put something here, 20 meter per annum. So that will be somewhat proportional here. And finally, we say in this case, if we have a sediment bed, that will mean that the sediment itself can be deforming And then I will draw it like that, which means over here we had what we call the till material, so sand, gravel, maybe loess, so some kind of sedimental material, and definitely not hard rock like granite that cannot deform. So in this case, if it is a warm base glacier, it's wet, there will be water flowing through here, this material, and then it will be able to be pulled by the ice. So I'll just put this component here as well and say that this can be, say, 10 meter per annum, just to be precise. So just to be a little bit proportionate in the drawing, I would say these numbers randomly, but these are then the different components that can be included. If the ice is on a cold base, then perhaps this whole component is going to be missing. So if it's a cold base, then this one might be missing. It cannot slide. We've seen those pictures when ice seems to be motionless in like Antarctica, in those very dry areas when only sublimation will cause ablation. At the same time, here if we say it's going to be something like a rock bed with a cold base, as well we can delete this one, so I just put it like this. But usually, to some extent, there will be a deformation, a transformation of the ice mass itself, thanks to the thickness of the slope. So usually this will be a component that will exist. But obviously, if the ice is not that thick, it's something just like that, perhaps there will be no motion because of the thickness. It's so slow. It's going to be slow because of this thickness is so little volume. So if it's compared to that one, something like this, maybe it's only like half a meter or so, because the ice mass itself will not add to this pressure. So this is just a little explanation about the integrated deformation profile. But again, what we will be talking about more in details today is to what extent this water, the wetness of the sediment bed, can contribute to the movement of the ice mass, or at all how this material can be later on be deposited. Also, we will be talking about how pieces of rocks will be traveling on the top, inside, and on the bottom of the ice mass. So we said that there's a supraglacial, there's an englacial, and subglacial, both water and both sediments that will be playing a role in forming our landforms. And also we will be looking at what is happening over here. So if we have something that is between warm and cold base, so the ice will be able to melt thanks to the pressure and then refreeze if the pressure is gone. So this is just a little bit of a recap and an introduction to today's class.